This video will cover the cleavage of ethers using hydrohalic acids. Ethers are not very reactive. This is one of the few synthetically useful reactions of ethers. This means that they make good solvents since they don't typically react with most chemicals. In this reaction, an ether is treated with a hydrohalic acid. This cleaves the ether to give two alkyl halides. Now let's look at the mechanism. Consider the reaction of this ether. If we treat this ether with hydrobromic acid, we will get two different alkyl bromide products. Now let's look at the mechanism. We're treating the ether with a strong acid. Therefore, the first step will be protonation of the basic species, which is the oxygen. This will give us the protonated ether and bromide ion, a good nucleophile. By protonating the ether, we've made a good leaving group, and this good nucleophile will react with the good electrophile, specifically the primary substrate. This good nucleophile will react with the primary substrate in an SN2 reaction. This SN2 reaction will occur more quickly than the SN1 reaction possible with the other side of the ether. This SN2 mechanism will produce the primary alkyl bromide product as well as the secondary alcohol product. The alcohol produced can react with another molecule of HBr, as we have seen in the past in reactions of alcohols, to produce the alkyl bromide. Just like we saw previously, the first step will involve protonation of the alcohol to improve it as a leaving group. This produces the protonated alcohol and the bromide ion. Next, the water leaves to form the carbocation, which will then react with the bromide ion in an SN1 mechanism to produce the alkyl bromide product. Typically, secondary and tertiary electrophiles, or substrates, will go through an SN1 mechanism, whereas primary ether substrates will go through an SN2. The identity of the hydrohalic acid is also important to determining whether cleavage of an ether will occur. HI, with its strong nucleophile, the iodide ion, will react in the cleavage of ethers most quickly, followed by HBr, with its fairly strong nucleophile, the bromide ion. Hydrochloric acid reacts most slowly, with its weak nucleophile, the chloride ion. Oftentimes, we won't see hydrochloric acid cleaving ether at all. Most ethers will react by the mechanism shown here. However, there is a special case of phenyl ethers. A phenyl ether is an ether where one of the R groups is the benzene ring. When phenyl ethers react with hydrohalic acids, we get a different set of products than we do with a typical ether cleavage. Instead of getting two alkyl halide products, we get the alkyl halide from one half of the ether and phenol from the other. We can figure out why this is so if we look at the mechanism. The mechanism starts similarly to what we've seen before, with protonation of the oxygen to produce the protonated ether and the halide ion. In the next step, the halide ion will react with the primary substrate, kicking off phenol. At this point, the reaction stops because there is no nucleophilic substitution possible at the sp2 center of the phenol. The ether still cleaves, but we stop with the phenol product.